You know, for centuries, some math problems have been seen as just fundamentally unsolvable. But what if the problem wasn't the problem itself, but the way we were looking at it? Today, we're going to look at a breakthrough that might just be a new key to a very, very old lock. Let's dive in.
Okay, just take a look at this thing. This absolute beast is an 8th degree polynomial, and our job is to find the exact value of x that makes this entire nightmare equal 0. This is the kind of problem that has had mathematicians scratching their heads for generations. Seriously, where would you even begin?
Well, struggling with equations like this is nothing new. It's a classic, deep-rooted problem in mathematics. For hundreds of years, we've really only had two main toolkits for trying to find the answers. And, well, both of them have some pretty major drawbacks.
And here's the fundamental trade-off. On one side, you've got the classical methods. These are all about finding perfect, exact answers using things like square roots, what mathematicians call radicals. The issue? There's literally a mathematical proof, the Abel-Ruffini theorem, that says for most equations of degree 5 or higher, this approach just plain doesn't work. You hit a brick wall. So on the other side, you've got numerical methods. Think of these as really, really smart guessing. They can get you super close to the answer, but they're always just approximations. They can have rounding errors, and you never get that 100% guaranteed exact value.
So you're stuck, right? Between a method that literally can't solve it and another that can't solve it exactly. It's a classic rock-and-a-hard-place situation. But this is where a completely different way of thinking comes in, one that promises to just sidestep these old problems entirely.
And this quote from the person who came up with the theorem says it all. This isn't just a small tweak on an old idea. The claim here is huge, that this theorem creates a whole new road to find precise, perfect roots for equations we thought were impossible to solve this way.
And that new road is called Ezouidi's theorem. What is it really? At its heart, it's a method that systematically breaks down a monster polynomial to find its exact roots. Now, the keywords you got to remember here are systematic and recursive. This means it's a step-by-step recipe, not a guess. You follow the steps, you get the answer.
So how in the world does it work? Okay, don't worry, we're not about to get buried in equations. We just need to understand the core idea. And it's less about mathematical brute force and more about a really clever, structured transformation of the problem itself.
The process is actually pretty fascinating. First, the theorem takes our original equation and kind of reframes it, puts it into a new language. Then, it defines a whole new set of special building blocks called symbolic coefficients. Now, step 3 is where the real magic happens. You calculate each of these coefficients one by one, and each new one depends on the last one you calculated. It's like a line of dominoes. And once they've all fallen, once you've calculated all of them, they basically just tell you the exact roots to the original massive puzzle.
Okay, now for the really fun part. Let's take this new theorem and throw our villain at it, that intimidating 8th degree polynomial from the start. What actually happens when we run it through this new process?
All right, the method gets to work. The gears start turning, and that recursive formula starts churning out results. It calculates those 8 special symbolic coefficients we talked about, one after the other. It's a pretty complex step-by-step calculation for each and every one.
And this is the moment where everything changes. This is where all of that complexity just gives way to the most incredible simplicity. Because after all that work, after all those nested calculations, a shocking pattern emerges. Every single one of those new coefficients is exactly 0.
I mean, just look at that. It's not an approximation, not some tiny number that's almost 0. It is perfectly, exactly 0 for all 8 of them. This clean, unbelievably elegant result is the key that unlocks the entire puzzle.
So what does it mean that they're all 0? Well, it means everything. It means the entire complicated structure of our original polynomial just collapses in on itself. All that complexity vanishes, and it reveals that there's just one single exact root that solves the whole equation.
And that number is 3. That's it. All those terms, all that complexity, the whole shebang, it all boils down to the number 3.
So to be precise, the one and only exact solution is x equals 3. And that multiplicity of 8 part, it's just a way of saying that this single root is so fundamental, it essentially counts as the answer 8 times over. The contrast, right, between this gigantic, messy problem and this simple, elegant solution, that's what makes this so amazing.
Look, finding one answer to one tricky problem is great.
But the real importance of a new theorem is what it means for the bigger picture. Why is this new tool such a potential game changer?
Well, it turns out this theorem has some serious superpowers. For one, it's universal. It doesn't care if the polynomial is degree 8 or degree 800. It also handles cases with repeated roots, like our answer 3, which can totally trip up other methods. And maybe most importantly, it gives you exact answers, no approximations, and it does it without using radicals. That means that old Abel-Ruffini wall we talked about, this method just casually walks right around it.
This table really drives home what a different way of thinking this is. The old methods saw repeated roots as a simple, kind of uninteresting case. This theorem actually reconstructs their hidden structure. The old methods get more and more complex as the degree gets higher. This one doesn't feel a thing. And radicals, the absolute core of the classical approach, this theorem doesn't even use them. It's a whole new playbook.
And that brings us to this final quote, which really gets to the heart of it. It's one thing to just find an answer. It's a completely different thing to explain it. The old methods might state the solution, but this theorem claims to do more. It reconstructs the solution, showing you from the ground up why the answer is what it is.
And that's a powerful idea, isn't it? It's a reminder that sometimes the biggest breakthroughs don't come from just trying harder at an old problem. They come from finding a completely new way to ask the question. It really makes you wonder, what other problems that we think are unsolvable right now are just waiting for the right perspective to come along and unlock them?